Neutrinos are amazing. Studying them tells us about neutrinos, of course, but it can also tell us about what they've encountered on their journey to our detectors. Can we use this to prove the Earth is round? That's what we're talking about today on Even Bananas. Despite what you may have been told, empty space isn't empty. There are all sorts of things floating about in it, including charged particles like protons that mostly come from exploding stars. When these crash into our planet's atmosphere, they kick off a chain reaction known as a cosmic ray shower. A bunch of particles are created, including pions, which decay to muons and muon antineutrinos. The muons will in turn decay into electrons, creating more muon neutrinos and some electron antineutrinos. So, for each pion, we're expecting 2 muon neutrinos and 1 electron neutrino, all of which continue their journey towards Earth. These neutrinos, created between about 5 and 50 kilometers above the surface, are known as atmospheric neutrinos. Atmospheric neutrinos are an important part of neutrino history because they were the first evidence for neutrino oscillation. To explain this, I'm joined by Dan Barrow, who is leading the atmospheric neutrino analysis on the Deep Underground Neutrino experiment hosted at Fermilab. Hi Dan.
Hi Kirsty. Just like accelerator-produced neutrinos, we know what type of atmospheric neutrinos we expect to see in our detectors. But unlike accelerator neutrinos, they'll come from all directions. So standing here, I've got some neutrinos coming to me straight from the atmosphere above me, and some reaching me having travelled all the way through the Earth. The neutrinos coming down from the atmosphere have travelled on average about 15 kilometres, but the ones coming upwards have travelled more like 13,000 kilometres before they get to me.
And if we're talking about neutrinos and distances in the same sentence, you know we're going to start talking neutrino oscillations. If you want a reminder on how oscillations work, check out this video. We can expect the atmospheric neutrinos created above Dan to show up with their original flavour ratios, but the ones coming from below him have travelled further and travelled through a lot of matter, which means they're more likely to have oscillated to different flavours, leaving us with different ratios.
This was first seen by the Kamiokande experiment in Japan in the 1980s, way before anyone knew about neutrino oscillation. They measured a muon to electron neutrino ratio much lower than the 2-to-1 expected, and reported, "We are unable to explain the data. Some as yet unaccounted for physics, such as neutrino oscillation, might explain the data." They showed that the deficit of muon neutrinos seemed to depend on the direction they came from, but didn't have enough data to draw firm conclusions. That was left to the next experiment, Super Kamiokande. Like Kamiokande, but more.
Super Kamiokande is a huge neutrino detector in Japan, full of water with detectors that pick up the flashes of light created when a neutrino interacts in the water. From the captured light, researchers can determine the neutrino's flavour and can also work out the general direction it entered the detector from. This means they can separate out the two neutrino populations, the atmospheric neutrinos that came from the near atmosphere, i.e. above the detector, and those that had passed through the planet to reach the detector. The data collected by Super Kamiokande showed that the flavour ratio depended on the angle the neutrino arrived from, and therefore the distance it had travelled. We tend to plot the data like this, showing the angle and the number of neutrinos detected from that direction. This was the first direct evidence for neutrino oscillations, and Takaaki Kajita was awarded the Nobel Prize for Physics in 2015 for this discovery. But Dan, the real question is, can neutrinos prove the world is round?
Well, the neutrino oscillations, or how they change flavour, is strongly dependent on the density of matter that they pass through. We can predict the flavour change depending on the path taken through the Earth and what we know about our planet's size and structure. So we're considering an oblate spheroid planet, i.e. a slightly squashed sphere, with an interior that has varying densities including a very dense core. Then when those predictions line up with our measurements, it makes a strong case for those assumptions about the size and structure being true.
Always useful to have one more piece of evidence that the world is round, just in case there's an argument coming. So Dan, is that it for atmospheric neutrinos, or is there more they can tell us about the Earth?
DUNE uses a liquid argon detector, meaning it will have better angular resolution and should be able to determine the directions of incoming neutrinos more precisely. For neutrino energies of about 1 GeV, which is around the peak of the atmospheric neutrino spectrum, DUNE's angular resolution is approximately 25 degrees, which should give us some decent improvements in our measurements. On top of pursuing its major science goals, DUNE may also be able to study the structure of the interior of the planet, maybe even measuring the densities of different layers in the Earth. At the moment, we're working on a full simulation of this to see what we can achieve. In addition, the neutrino oscillations are specifically dependent on electron density rather than just simply mass density, and this is something that traditional seismology can't access. And although other experiments such as KM3net are also trying to study the Earth's core with neutrinos, at the moment their sensitivity is too low to resolve any fine-scale details. We're hoping DUNE will be able to improve upon this and shed new light on our planet's structure. At any rate, DUNE will be doing atmospheric neutrino measurements from day one, so watch this space.
Thanks, Dan, and good luck. So there we have it, our friendly neutrinos added to the overwhelming evidence that the world is round. And with DUNE, our favourite high-speed seismologists might be able to tell us even more about what's going on beneath our feet. Don't forget to subscribe for more of your favourite neutrino content. Fun fact, the amount of atmospheric neutrinos we expect to see changes over the year. And just like us, neutrinos turn up less if it's too cold out. The IceCube Neutrino Observatory based in the Antarctic sees about 4% fewer atmospheric neutrinos in the chilly depths of winter compared to the annual average.